Good morning, everyone. Today is March 14th, 2020, and this is the John Chappell Natural Philosophy Society Science Chat. And if you're watching the recording, thank you for watching. Let's see here. So who do we have here today? Today we have Ian.
Hello,
and James. How you guys doing? So here we are in the science chat. Let's see here. We only got 3 people at the moment.
I always have to remember, Franklin, to come an hour early because our clocks don't go forward until the end of the month. So you're starting an hour earlier for me.
Oh, okay. That whole, daylight savings time thing. That always seems to catch me off guard.
Same here.
Especially in the, I guess now the spring, but the fall. It's like I'm always like showing up like an hour early to something. It's just...
Spring forward, fall back. But I think within a year or two, we'll probably cease doing it because of European Union requirements. And the UK probably will continue. So we'll have an hour difference between Great Britain and Ireland. Anyway.
Yeah, are they really considering that? So you're saying in the EU, because I've heard about them maybe doing that in the United States, but, not really. I mean, it just seems like a real pain to run around and change all of our clocks. And I just happen to always look at the clock that hasn't been changed, thinking, oh, well.
Yeah. Do you know where it started? A lot of people are not quite aware exactly where it started.
Wasn't it Benjamin Franklin's idea or something?
It was Benjamin Franklin's idea and others, but it didn't start till 1916. And it was started by the German Empire during the war to save coal for generating electricity. Because in the summertime, excuse me, they had these very long days and people were sleeping for hours and hours. So they said, well, why don't we give them more time in the evening? So they put their clocks forward an hour in April 1916. And their enemy, the British Empire, a month later did exactly the same, May 1916. And then I think America followed, about 3 or 4 years later, and other countries.
Oh, so this is the Germans' idea, huh?
Yeah.
So Ben Franklin didn't actually implement it. He just said
he didn't implement it. It was his proposal very early on, of course.
Uh-huh. Well, then, he shouldn't deserve the credit. It's people who actually put it into place should deserve the credit. So I didn't hear about that story.
See, the government could say to people, look, I really think you should get up an hour earlier in the summertime. We're ordering you to do that. But of course, people won't do it. So the way to force them to do that is actually change the clocks.
Yeah, that's exactly it, right?
But the European Union, to get back to your question, I think their directive is that they will get rid of it. I don't know, 2021 or 2022. But it's left up to the member states as to whether they continue with winter time or with summertime. So it's going to be rather a bit of a jumble, I think, because people, for example, we had an experiment between 1969 and 1971 where we kept Greenwich Mean Time. Sorry, I beg your pardon. We kept summertime throughout the year. And in the 2 winters, we were sort of dark until about 11:30 in the morning. It didn't get dark as early in the evening, obviously, but it was quite dangerous for the school children and so on. So I'm not very much in favor of it. I suppose I'm so used to the daylight saving time. I'm quite happy with it.
Yeah, if only all our clocks would change. At least our iPhones automatically change, right? Anything which is internet connected usually does the right thing.
That's true.
Although I did have my satellite enabled clock, that they're supposed to automatically do that. And that's what caught me last year, is that it lost the satellite signal. So it was like the one clock in the entire house, which wasn't set. I was thinking it would set itself, and that was the one I was like paying attention to when I woke up. Oh, well, it's time to go. But really, it wasn't. So this year, I made sure to stick it outside and made sure it got the satellite signal, and then it was coordinated with the rest of the clocks.
But of course, we're very centric to our own practices. I mean, I just indicated a practice now which can catch us out between the United States and Greenwich Mean Time. You've decided now to change at the beginning of March. And similarly, I think at the beginning of November, you go back. Whereas we changed the last Sunday of March and we changed the last Sunday of October. So there are a couple of weeks where there's an hour less in the time difference. And then you could be in other areas, other countries that, like, for example, Singapore or Thailand or something, that don't change at all. Or you could be in other countries where they have half hour differences. So we're sort of centric to our own practices.
Well, then it's a miracle you showed up here on time, right?
Every other year, do you know what? I've come in the middle. I've said, what are they talking about? I'm halfway through the conference. And it happens on both occasions, actually, if you think about it, because you'll be an hour earlier than we are for, there's 4 hours difference between New York and Greenwich now instead of 5 hours. And similarly for about 2 weeks in the autumn. But it's just happened to me so many times. I said, I better remember. So, do you know, I actually went into the internet to see what time it was in New York at sort of 11 o'clock this morning. And I said, yes, only 4 hours. I better be ready at 2 o'clock here instead of 3. So it is a miracle, but I managed it this time.
All right. So Moose there says summertime switched on by ether direction. Not quite sure what that means, but maybe he's saying that we should start talking about, science rather than time. Although time is another topic we typically talk about. I was wondering, so we got James here. I'm not sure we talked to James too much about time. So I guess you have your theory. So how do you feel about time? I think you think that time is quantized, right, versus continuous.
That's correct.
So what do you think quantizes time?
What do I think quantizes time? Well, the same thing that quantizes space and energy. Those are the three items which are quantized. Those are the three units of measurement where we have mass as a measure of energy in kilogram units, length in meters, and time in seconds.
But the question is, why would those three quantities be quantized? Why not continuous? Why can't you have infinite variety of amounts of time or energy or space?
Well, there's an old saying, by their fruits ye shall know them. Okay? And so when we postulate something in science, does it bear fruit? And there are a number of victories of binary mechanics which can be listed. I mean, there's actually dozens of them. But probably the main one is the ability to derive the unexplained data known popularly as the fundamental physical constants, okay? And binary mechanics is the only physical theory, which comprehensive physical theory, that does that, okay? And that's just one of the fruits. So it's why quantize anything, okay?
Well, that's not really the question. The question is, why would it be quantized? I'm looking for a physical reason, or you can also just say that it is postulated.
Well,
that's
I'm
perfectly
saying
fine to say that as well.
I'm saying that it's just postulated, and when you quantize those values, you get a stable universe. Now, with the previous quantum theory, which lacks the quantization of these three items, so ironically, what we're calling quantum mechanics and quantum theory in today's physics is incomplete quantum theory or partial quantum theory.
What
Um,
exactly is quantum and quantum mechanics? Then, I mean, they must think something is quantized.
a value which takes integer values. In other words, it cannot be represented on the real number system unless you reduce it down to the subset of the real number system, which is called the integer scale. For
Yeah, but
example,
what do they
electric
reduce to
charge.
integers in standard mainstream quantum mechanics? Because, well, first of all, when anyone says quantum mechanics, I don't know what the heck they're talking about. That could be anything, just about. But what do you think they're into? What takes the integer value in mainstream
Well,
science? I should say.
prior to binary mechanics, things like the orbitals of the electron, the electric charge itself. Okay, the elementary charge, what's called the elementary charge. And so when you say why quantize anything, uh, is is that it produces results. It
Well,
explains.
I'm not asking the I guess this is a subtle question. I mean, there's, why quantize thing, but I want to know what is causing that quantization. Like I said, you can say that that's just observed and postulated, or you
Well,
could try
that's
and come
the
up with
next
an
step in
explanation.
science. In the case of images on our computer screen that look very real, I mean, they're very high definition, high quality, and they look very real. We know who created those images. It's people. Now, who created the quantized universe, the binary universe that we live in, is of course a little bit beyond us at this point in time.
Well, I mean, I would
It's
provide.
beyond me anyway.
See, I would go beyond that. I would say that it's not a postulate that these items are quantized, and there could be some reasons behind them. Now, it's one of the possible reasons is that we all live in a computer, and that computers run at fixed clock rates, and behind every computer there's a crystal, and that's clicking away at like 2.4 gigahertz, and nothing in the computer can happen faster than 2.4 gigahertz. By each clock tick determines a unique state of the computer that goes on. So if you were
Okay,
to
I
ask,
would call that, Franklin. I'm very sympathetic to that sort of a description. I would call that just another way to say that we're quantizing space, time, and energy.
it is, but I'm saying
Uh,
that's a possible physical explanation for why the quantization happens. So that's one. If we live in a digital computer, then
why it
obviously
happens.
we know everything in a digital computer is quantized. Time, especially, is quantized in a digital computer, and the presence of an electron either here or there is also quantized. Like an electron can't be half stuck between a gate and a transistor. It's either there or it isn't, according to the quantization of time. So that would be an equivalent of like quantization of time and space, right? Space being whether an electronic bit is a 1 or 0, the space in the computer being all the bits, available bits and registers in a computer. So that would be one way that I like to think about, why does this quantization, because we can observe the quantities, well, to a certain extent, we can observe the quantization. You mentioned the quantization of charge, which is another interesting question as why is charge actually quantized, or did someone get that wrong? Some theories say that, the electron's made out of like 3 smaller, strings or whatnot, and would predict the presence of, say, a 1/3 value charge, or quarks. They do that. They would predict the value of 2/3 and 1/3 charge being possible, but we have never ever observed such a thing. So that would be kind of those are questions that I think need answers. And as dissidents, we could just say, oh well, that's just the way it is. Electron has got a fixed charge because it's got a fixed charge, and not worry about that. Although that tends to be what we worry about. So,
well, by quantizing the space-time and energy, is from those basic starting point, if you will, enabled me to derive the electric charge value from the scalar bit operation, which is one of the time development operations in binary mechanics. And these 4-bit operations, which are scalar vector for magnetic and unconditional and strong, these 4-bit operations are what are like a cycling program, if you will, that is implemented over the quantized time intervals, and which makes the universe tick along. Now, the whole question of why that is it a big computer and so forth, I think is getting a little bit more from science into philosophy. On the science level, I'm just sort of ad-libbing here because I'm not sure that I've really thought this through myself even completely. But on the science level, I consider the quantization of space-time and energy as postulates which have a certain utility. What is utility? How is that defined in science? It produces advances in our knowledge and understanding. That's a measure of, or a concept of the utility of an idea in science. Now, why we have the world that we live in, we could go to Dr. Seems to be sliding into the area of philosophy and even religion. So I'd rather just stick with the science. We're postulating X, Y, or Z, and what fruits does this bear? What advances? So that there are certain things which can be readily explained, like the photoelectric effect, by assuming a quantized electric charge and some other values which are also quantized, and in terms of photon energies and so forth. And the utility is that it explains a number of phenomena in a way that we can then control and use these phenomena, design things that use the phenomena. And that's the utility in science. And humans, I guess, will always be asking, whatever it is we say is the most basic thing in science, humans are always, I think, going to be asking, well, what caused that most basic thing? Or what is that based upon? And that's true, but my work, I think, is going to stay mostly in the science realm, and I'll leave the philosophy and the explanation as to why on a philosophical or religious scale, if you will, to others. You could just say, as Bill Lucas does, well, there's God. That's it. And he just stopped short. When Franklin has and others have asked Bill Lucas this same question in the past, he immediately jumps and says, well, that's what God created, end of story, period. That's not exactly where I'll go, but my work is is the science criteria, which I'm calling by their fruits ye shall know them. What is them? A postulate that makes sense. Okay.
Well, some of those postulates, I think, are pretty complicated. Although now, as a skeptic of binary mechanics, now you say you derived all these constants, although you knew what the value was before you derived them, right? You knew what the answer was.
I knew that they were measured values. I knew that there was organizations like the National Institute of Standard, NIST, in .gov, that have these constants, and a kilogram is so much. The speed of light is so much. But all of these are unexplained data. In my view, they have been wrongly presented in science and to physics students as fundamental physics constants. Now, what does that mean, fundamental physics constants? Well, a lot of these constants, like the speed of light, appear in various useful equations in physics all over the place. And so therefore you might say, okay, they're fundamental. But that does not change the fact that these are unexplained observations. Why is the speed of light not in vacuum, not 2,000 or 200,000 meters per second instead of about 300,000? Why? These are unexplained constants. They're measurements that people have made. Measurements such as the
well, we know about that, although that wasn't really the point. The skeptical point I was making is that we have these constants. The thing is, as dissidents, we have the answers. And I've seen in many cases people making similar claims where they can replicate existing data. It's basically a post-diction versus a prediction, but it's kind of hard to predict something that hasn't already been measured, I suppose. But I'm just saying, as a skeptic, what would you say to the argument that the reason why you can do that is because you simply designed your system to spit that out? Because as a computer scientist, I know I can make any program do anything I want, and with sufficient futzing.
Oh, that's a really good question. For example, the values for the three, what I'm calling primary constants for mass, length, and time, these values were assigned sort of in a reverse engineering process to allow the same to be used in the equations showing how we derive Planck's constant, elementary charge, the electron intrinsic magnetic moment, the speed of light, and so forth. In other words, they were selected so that all of these equations worked simultaneously. In other words, those values could have no other value, okay, unless the math was completely wrong. And the math I'm using is algebra. It's not even up to calculus, okay? So now with the speed of light, the most recent paper I published in the Journal of Binary Mechanics, the free online journal, it uses the time development laws of binary mechanics, and it simply injects on one side of a cubic volume, a signal of quanta being injected into the volume. On the other side, we're measuring the quanta arriving there. And then we just run the simulator. And guess what? It turns out that it gives us the speed of light. And the speed of light, according to the equations that I published, it's called the constant derivation tree. Excuse me. Is 1 over pi in bit velocity units, or in other words, bit velocity is the length constant divided by the time constant, and that is approximately pi times the speed of light. Okay, so in other words, if you want to know what the speed of light is in terms of the fundamental constants, it's simply bit velocity divided by pi. That's your vacuum speed of light. Now, so that we're
although that still really doesn't address the objection, because actually you just kind of admitted to how you do this, which is basically reverse engineering. You start with the constant itself. You come up with a model that is basically the parameters have been fine-tuned to match the known constants, and then there's no wonder why it predicts that exact same constant because that's what it was designed to do.
Well,
Right.
there's nowhere in physics literature except in binary mechanics work that you're going to find that the light speed is the bit velocity defined as the length constant divided by the time constant over pi. Nowhere.
Well, that might not be true because
So
these,
there's nothing
because
being
well, I
exactly
mean,
fine-tuned
physically,
here.
physically, I would say that that's actually false. I mean, that's known false because the speed of light is generally determined by there's like two constant, there's like the permittivity and permeability, and you can predict what the speed of light through any material would be as the ratio of those two properties, whatever the heck permittivity and permeability is. So it's not.
Well, that's circular logic. By the way, in binary mechanics, we're so happy you don't need either of those values. Those values are supposedly describing properties of perfect vacuum, and that's a complete fantasy. That's in 20th century physics. But here we are now in the 21st century. We don't need those anymore.
Well, I think permittivity and permeability are definitely two measurable. I mean, magnetic, the like permittivity. I forget which is which. One is like the ability for that particular space to accept magnetic activity, and the other one is something like the effect of accepting electrical activity or something like that. It's kind of one of the reasons why people think EM waves have something to do with electrical and magnetic properties, since the things that it depends upon are those things. I mean, you have to be able to predict that the speed of light can change under varying conditions. Now, those varying conditions seem to be having to do something with electrical and or magnetic properties of the space that you're dealing with, right? So if you came up with the speed of light being actually constant, then that's wrong because the speed of light is certainly not constant. Under different gravitational conditions, it's known to be not constant. That's one of the things when people talk about relativity, they say the speed of light is constant. Like, no, the speed of light is not constant, right? Through water, the speed of light is very much different, right? It changes speed, right? So trivially, the speed of light is not a constant in any way, shape, or form. It's certainly a completely variable
That's
thing.
consistent with but below a quantum density excuse me, of about 0.1 of maximum possible energy density, the volume of space is opaque to light. Light doesn't transmit through it at all.
Let's see, you're kind of breaking up on me here, James. Ian, can you hear him okay?
Yeah, I was just about to say, Frank, the James has become distorted in the last few seconds. Very distorted.
Everybody is breaking up.
Am I distorted as well? I could hear Franklin clearly, but not you, James.
I guess we're all distorted.
They're trying to cut you off, James. You're getting too close to the truth, right? Yeah, this conference is carefully monitored by the Black Ops.
I can hear Franklin clearly, and you can hear me clearly, Franklin, can you?
Yes, I can hear you clearly.
So I think it's a problem with your system, James, unfortunately.
Yeah, they're slowing him down there. His internet connection is being slowed down. He lives in the Caribbean island, so, who knows what's going on over there. Let's see here, but let's see.
You're breaking up. You're sort of breaking up, Franklin.
Yeah, I think that between me and Ian, we're fine. So we're thinking that your internet connection is slowing down. Maybe you could possibly turn off your camera to reduce your bandwidth. Let's see here. We got a few. We've got a few comments in here. Let's see here. So you say you can probably quantize time by waves traveling around nuclei or like that. although it would take time to travel around the nuclei. So I don't think you could use that as the fundamental unit. See, I'm thinking the fundamental unit is that you have to take space and you have to quantize it, as if you're putting everything on a graph paper, or pretend you're like in Lego world where the brick can only appear in one place or the other, right? And that quantization of any movement at all, would be what you would have to quantize, I would think. If you have something going all the way around something, then that's definitely taking different spatial positions in order to do that. So that's what I would say about that. Now, if anyone else has any comments, just feel free to jump in here. I see we also have Alistair and Carl with us. So if you have any comments, I do believe I have you on the stream. So another comment, that time can be dilated, contracted. Those waves can be interrupted by close by waves from other particles, as well as wave compression by acceleration. Now, time dilation is an interesting topic. I mean, what exactly is going on with time? See, a comment like that would tend to indicate that, you know, time as a whole might be, say, dilated. That if I dilate the time right here in front of me, that I would be dilating the time in front of Ian. But that obviously isn't the case. I think when you're talking about time dilation, what you're really talking about is clock dilation. Time itself, I don't think, can be dilated in the sense that it would change for James and Ian and me simultaneously, right? I think that's the only way that time, as being a thing that happens across the universe, could possibly said to be dilated, right? So I think that what we're talking about, time dilation, is actually a local phenomenon, which is clock dilation. Like, if given any given clock, if you go and you accelerate that clock, you will find that that clock will slow down compared to one clock which is not slowed down, right? And I also kind of, as an analogy, say that if you were to put a piece of meat on the counter and put a piece of meat in the freezer, and you would find that the meat in the counter degrades much faster than the meat in the freezer, that the freezer is not undergoing time dilation per se. All it's doing is slowing down the chemical reactions, and the meat is not time traveling. It's just, you know, it's natural processes is just simply happening slower, and that's what happens with these clocks. The natural process, whatever it's doing, those things happen to be going closer there. So again, I'm not sure that I can agree with time dilation having to do something with waves. That see, we get some other comments here. No, I think it just showed that one. So according to Hawkins, Stephen Hawkins and Moldenov, the user might be analogous to Conway's game of life. The next state is solely dependent on the present state. That sounds like quantized time. Yeah, I think it certainly does. That as time ticks forward, or if time is like a computer, or if like the galaxy is like a computer, then the next state would generally be solely dependent upon the previous state. So, but I was thinking that I don't think that idea, though, is philosophical. I mean, actually, they have entire conferences dedicated to this idea that that we are in a simulation, right? So they have all these people gathering together. But the science part would be to prove that that actually happens. So certainly one way of doing that would be to run experiments to, say, find the time quantization, which I think it would be a possible experiment. You would have to prove that you have an experimental setup that can set up arbitrary bits of time, and you just keep on slicing it down until you get to a point where you cannot find a smaller bit of time in any physical system that this experiment covers. And then that would prove that time is quantized. And then you could prove that you could observe, say, an electron, and you could prove that the electron cannot move faster than your quantized time bit, right? By whatever means you do that. And then perhaps you could then show that no matter what you do, the electron cannot move more than one integer distance during that quantized time. Would be another way of demonstrating that there's quantization of space and time. That would be relatively easy. Now, I have been thinking that that could be measured if you could measure the actual transition of an electron around a hydrogen atom from like level 1 to level 2. So from level 1 to level 2, I'm thinking demonstrates the quantization of space. So that's definitely an integer quantity. The electron can only be distance 1, 2, 3, 4, 5 away from the nucleus. So that in itself demonstrates a quantization of space, right? That's the only reason why I think electrons take these shells, right? I don't think they're orbits. That's the major thing that I think is different. The electron is not ever orbiting the nucleus. That doesn't make any sense. But what it can do is that it can take integer steps away from the nucleus. And the reason why it's taking integer steps is because space itself is quantized. So it can only go, 1, 2, 3. It can't be 1.5 or 2.5, right? So it can be at 3, and then it jumps back to 1, and then that releases a quantized amount of energy, which we perceive as light. So just around the hydrogen atom, if you could figure out the exact distances you're looking at there, that would determine the smallest bit of space. And the amount of time it takes it to go from 1 to 2, that should determine the smallest amount of time. So I think these electrons are moving at the fastest possible speed using all of the available quantized steps for space. At least that's what I've been thinking. That's that's my dissident thought as to how we could precisely identify what is the step of space and what is the step of time by observing the hydrogen spectrum. But the other thing I've been thinking about is that if that were the case, then the hydrogen spectrum should be completely immune to relativistic effects. So I was thinking, well, if you take the hydrogen atom and you accelerate it, does its spectra change, right? I'm thinking it wouldn't. It should be fairly immune to that sort of thing, according to my theory, but I've not particularly heard about whether the spectra of the hydrogen changes if under, say, high gravitational influence or velocity effects. You'd think that'd be something that would be relatively easy to measure, and someone may have done it. Maybe I just have to Google it and find out. Because based on my feeling about how time and space is quantized, that would be something I would predict. I'd also predict that if you built an atomic clock, actually built out of using the time frequency, the time it takes for an electron to transition from one level to the next, that you would find that clock would be completely immune to relativistic effects. Well, except that maybe it would not be immune to. Well, I know. I think actually, even under gravity, it should remain immune, and certainly under velocity effects, it should remain immune. So that we could show once and for all that time is absolute and that relativity sucks, because you can find an absolute time frame reference. That's all we have to do to make relativity go away, I think. Here we have a comment about kindergartens here. It says, I think most kindergartners think this way, that the next state is dependent upon the present. Well, certainly that's how we perceive time, right? If I fall off a tree, it's because I climbed up there in the first place, right? I don't find myself falling off the trees just for the heck of it. So gentleman asking the opposite question: what would the universe look like, for example, if the charge of an electron was continuous? Well, maybe I'll ask James that. Maybe, if time were not quantized, I mean, if stuff was not quantized, what would the universe look like? So let's see here. Let's test your connection again. Are you there, James? No, I'm not.
I think
hearing
James
you.
has come to the conclusion that the problem is indeed at his end.
Well, what about you, Ian? What do you think would happen if these things weren't quantized?
Well, I was thinking that I frequently express this as the question as to whether the universe is analog, Franklin, or digital. I mean, if you have these continuous type signals, or if you have these signals made up of discrete elements. And I don't know, I really have an open mind. Time analog, not digital, no step, only a minimal ratio, depending on frequency. Sorry, just reading the thing there because it was about what I just said. But I'm not convinced. Sometimes I tend to think that this quantization goes a bit too far. We have to be a bit cautious. Obviously, it appears that the Planck radiation law does require a quantization in regard to the propagation of energy, and that seems to explain the distribution of energy over the various frequencies or wavelengths. But people have all, like Bill Lucas or something, has talked about Bode's law as being a quantization as well. So you can extrapolate this to various things. And of course, James has his binary mechanics, which I need to spend more time. I've spent very little time even looking at it. So I need to spend more time before I can maybe talk about that with any authority. But I'm sure, to answer your question, we could conceive of some simple experiments if we just put our minds to it, Franklin, which could distinguish between a sort of an analog universe and a digital universe. The fundamental sort of processes of nature.
Well, I think mainstream, I think the quantum, I suspect, of quantum physics is exactly that situation I described about the spectra of the hydrogen or of any element, right? Because that's always been the question, is that when you excite these gases, they only put out very, very specific frequencies, right? So if the electron were continuous, that thing that's going around the hydrogen atom, if that could take on any value, then I would think that the amount of energy it might generate going between levels would also be continuous, right? So instead of seeing, a line here, there, you would expect a continuous spectra, right? Maybe some would be less, some would be more, but you would expect the spectra to be continuous. But we don't observe the spectra to be continuous. We observe it to be extremely discrete. So I think they named the entire science of things down in that area of atomic physics to be quantum, largely because of that. But
there are discrete divisions, or cancellations, if you like, in the spectra. But I mean, the spectrum is really continuous. In fact, we talk about there being these discrete divisions relative to a continuous spectrum, and otherwise continuous spectrum of the of the various colors. So I'm not sure per se if the thing is discontinuous.
Well, I'm talking specifically about, because if you look at the spectra that are coming from the sun, that's pretty continuous, right? But if you look at, if you've seen these demonstrations where they take like a tube, and then like a tube of hydrogen, and they ionize it, and it glows, and then they put it through basically a prism or spectrum splitter. You see it only coming out at specific frequencies, which is kind of strange. Why is it? It's like a light bulb that produces exactly one frequency or two frequencies, or in the case of hydrogen, it produces only like three visible lines, and so the spectrum is completely discontinuous. So that's something that you could look at. That in fact, probably I can find a quick reference to that in Wikipedia, I suppose, and get a picture of
that these discontinuities, and maybe including the one you just mentioned, they are anomalies. They appear not to be fundamental aspects of nature. I think they're anomalies from an otherwise continuous system.
No, they're not. They're definitely not anomalies here. Let me see here. Why is that? I can't find. I just want an emission.
No, but I mean, you're drawing attention to them in that they are different from an otherwise system in which you would not observe these discrete elements. It's not the norm. It's something that you're pointing out.
Well, it's definitely, you have to get a very special setup to get the spectra. So you guys can see my screen?
Yeah, I don't know if you increased it a little, but yeah, it's fine. Otherwise,
but this is the emission spectra for hydrogen. So you can see it produces just this one bright red line at 656 nanometers, and these other 4 lines to the left. And that's it, as opposed to a continuous spectrum. So a continuous spectrum would kind of be like what they have here in the bottom here. That's what you would normally see. That's what comes out of, say, light bulbs and sunlight.
Well,
and the glowing objects.
Spectrum there with absorption lines.
Those are absorption lines.
And then what you've shown is the opposite. You only have positivity where it's actually being transmitted through the medium. Black.
Well, they get the negative. Let's see here. If they put all the light through something, and then the lines that would normally be emitted are absorbed. Now, I'm not exactly sure how that works, but they also have the spectra here for some other elements. Yeah, so that's the hydrogen in the top there. In the middle, we have mercury, and in the bottom here, we have neon. And so your neon bulbs, you always notice that they have like kind of orangish color. That's because a lot of those strong spectral lines are in the reddish zone. But I'm just pointing out that this is, if you've not seen this before, this is the quantization of, I think, quantum physics. That we see these very, very specific things. And I'm saying that this quantization is actually evidence of the quantization of space and time, because that's really the only way these things could be limited. Because if the charge was variable, if the amount of space that an electron could travel through was continuous, then you would not be able to see this kind of thing. The only way you can get this is if you, if you look at the Rydberg formula, it's just like 1/r² minus 1/r². And all that is actually just an expression of Coulomb's law, right? Coulomb's law says the force, electrostatic force drops over 1/r², right? And you just say the distance of r is 1, 2, 3, or 4, 5. And the amount of energy that you see coming out of the system is just, you subtract the energy difference from one level, like if you're at 4, that'd be 1/4² minus, if you're going to level 2, 1/2². That's Rydberg's formula. which is also just expressing the difference in potential energy of Coulomb's law if you were to presume that the electron can only jump integer distances away from the proton. And so Rydberg's formula wouldn't exist if none of these things were constant, right? But I think that's sort of my attempt at answering this question about, what would the universe look like if these things were continuous. I think the other problem that you would get, and that the problem that quantum physics really runs into, is that when you try and calculate anything, you get an infinity, right? So that was kind of the ultraviolet catastrophe, I guess, that if you look that up, that the amount of energy available at the very highest frequencies would be infinite, right? And it's not. So that's why they say that that energy must come in a smallest part, right? That's Planck's constant, I think. The energy must come in a smallest piece. Otherwise, energy would be allowed to go to, infinite. If you get an infinitely small time for frequency, then you can have infinite amounts of energy, and we just don't see that. So that would also be a evidence of must be a quantization of space and time. And I really believe, actually, Planck's constant is just basically an expression of the amount of energy that I think a single cycle of an electromagnetic wave can have, because that would be like the smallest thing, like the smallest bit of energy you can get is from an electron transitioning from level 1 to level 2 and then back again. I think that would probably be the smallest bit of energy that you can possibly get. And then everything else has to be multiples of that, right? So once again, that is an example of proof as to why the world could be is not analog, which can have all these continuous values, but rather it's more digital, that it can only have these very highly quantized values.
I mean, just looking more basically at mechanics, if you like, if you have the old paradox of Achilles and the tortoise, the Zeno paradox, where the tortoise, has a gain on Achilles, and then Achilles starts. Well, if you look at this in a purely digital way, Achilles will never overtake the tortoise, because when Achilles obviously is at the place that the tortoise started, the tortoise will be a little bit further on. And then when Achilles is at that position, the tortoise will be a little further on, and so on. So you can never overtake him. But if you look at it from a continuous point of view, you get a sort of a limit, sort of a limit of an infinite number of infinitesimally small elements, which we use in differential calculus. And then you find that he does overtake him. So that might indicate that it's a bit hard to move away from an analog model for fundamental space and time in dynamics, I suppose.
Analog model, okay. Let's see, we've also got Jim. So Jim, I've added you onto the stream. So if you have any comments, you can just unmute yourself and talk. I guess we've been talking about time, and that's this whole thing kind of started about because of the whole daylight savings time thing. So we kind of got talking about time here. So some super fin guys, you didn't explain the speed of light a long time. It's just the propagation speed of the ether. Yeah, I would totally agree with that.
Well, it's the propagation speed in the ether, if you like.
Yeah, it's the propagation speed of the ether. Which the question is then why is it that? I mean, the propagation speed of lots of things are different, right? If you take the speed of sound propagates differently in air and water and steel. But we know what the formula for the propagation of sound is, and it depends on the elasticity and the rigidity, I think, of the material. So there's those two properties, and it's like 1 over the square root of something of the other, and that expresses the speed of sound through any medium dependent upon these two fundamental properties, right? And so that was bringing up with James, and that light has exactly the same formula for the speed of light dependent upon these two properties, permittivity and permeability. So I kind of wondering, what is really these two properties? Is that exactly analogous to stiffness and rigidity that we know that belongs to in the formula of the speed of sound? In which case, the speed of light is really the speed of sound through whatever the space medium is. Now, other people like the Epola people believe that space is filled with a positron-electron sea. I also believe that as well. And they've done sophisticated calculations because we know what the properties of positrons and electrons are, right? And we know what the binding energy of those things must be because we can see what happens when they come together. We can tell the amount of energy it takes to pull them apart, like from the E equals mc squared. So if you make those presumptions, presume it's a solid, then you can calculate what the speed of sound would be through that solid. And they come up with, oh, well, that just happens to be the speed of light, right? So the light, we're talking about that being a constant, but it's definitely not a fundamental constant because it can definitely be calculated as the result of two other measured properties, right? So that's not a fundamental constant at all.
Or just advocating it from the opposite point of view, I think the mainstream might be justified to a certain extent in saying, well, there are three constants, and not three are fundamental. That is true. Two of them would be. So what they do, they tend to define the speed of light as a fundamental constant, and the permittivity as a fundamental constant. No, sorry.
Some of those values are actually
permeability is a fundamental constant, and then they derive the permittivity. But it's a bit arbitrary what they do. They define mu naught to be 10 to the minus 7 exactly Henrys per meter.
I think true constant would be like the mass of an electron. That seems to be that is not derivable from anything. I'm just saying that things like the mass of an electron is much more a fundamental constant than, say, the light. Light is a very complex thing. Like maybe Planck's constant is an actual constant. I'm just saying that light is not a fundamental constant. I mean, light is definitely something that changes. Speed of light is definitely something that changes. So that would be my only argument there, is that light is not constant. Whenever anyone says that light travels at the same speed, it doesn't even do so in a vacuum, right? It doesn't travel. Speed of light travels differently in a vacuum here on the surface of the Earth than up in a GPS satellite, for example. But it definitely travels at different speeds under those different circumstances.
Well, there are two things there, perhaps. One is the observed speed of light does vary. That is true. Well, I'm being unorthodox now, but depending upon the motion of the observer, that does change the speed of light. So that's against the special theory of relativity. But yes, but the second thing, and I'm not sure which one you're referring to. You might be referring to both, Franklin. But the second thing is depending upon the properties of the medium again, this is unorthodox, through which the light is traveling, you get a different speed when the observer is stationary with respect to the medium. So, for example, as you point out, if you had water or glass, you would get a different speed if you change the refractive index. But also, if you have something like an electromagnetic wave bouncing against the ionosphere, you have it's sort of a 180-degree change in the phase. So the phase velocity of that ray actually exceeds the phase velocity of a ray in empty space, empty still space. So there are two reasons why the speed of light varies. That's true.
Well, there's a third one, and that's gravitational potential.
Yeah, gravitational potential definitely affects.
My question
Speed of light.
is there any way to determine how that would affect the permeability or permittivity?
Well, you could work it backwards, I would suppose, because if we know what the formula is for the speed of light, burst time, permittivity, and permeability, so you would have to say that one of those two constants must be changing, right?
Or maybe
under a
both.
gravitational field, or it
maybe
could be
there's
both. Yeah, it could be.
So how do you calculate that?
I
Well,
think we would
seen
have to
anyone that's-
measure those because we could measure those properties separately.
I mean, I don't know if this answers the point, but I was in correspondence some time ago with Akinbo Ojo, and it wasn't made very public. We kept it maybe just to a few of us, but because it was at the time that I was talking about the Eddington experiment, and calculating the diffraction of a ray of light glancing the sun owing to the gravitational effect. And basically what I use is I just use the Newtonian formulas, the differential equations and so on. Now and I got a value which was the Soldner or Newtonian value, which was 1/2 of Einstein's value. But what Akinbo did is he looked at it, I think, in a way which is a bit nearer to the way you're looking at it now. I'd have to look up the details, but he sort of said, well, look, let's take that the deflection is such and such, and then let's work backwards to see what the effective change in refractive index would be. So it's another way of looking at the thing.
Well, Howard Hayden actually derived how you can get the bending of light by assuming that the speed of light is affected by the gravitational potential as 1 plus phi over r. So
I think
that's
that
assuming-
might be near what Akinbo was doing, actually, Jim.
yeah, others have done it, and also so that the speed of light gets slower as you get closer to the surface of the sun, and then speeds up again.
Well, talking about the
And that also explains the Shapiro effect. And in fact, I just read something on ResearchGate yesterday about how one guy tries to say it's just the speed of light is constant, actually, but the other guy says, well, it doesn't explain the Shapiro delay, which actually makes it makes the light take even longer to get back from reflecting off a spacecraft at opposition. That would have to be explained as the actual speed of light getting slower as it grazes the sun.
But do you remember, I mean, say following Hayden's work and so on, phi over c squared and so on, whether he got the value of deflection, which is predicted by general relativity, or whether he got the value which is predicted by Newtonian physics?
It's general relativity. In fact, that's what Einstein used to calculate the deflection.
Okay, that's something I dispute, by the way. But anyway,
What do you mean?
Talking about light traveling different speeds through different medium, one question I've always wondered about is is what is the difference between medium that transmit light and media that do not? So like a solid block of steel does not transmit light, but a glass of water will, or plexiglass will, or glass will. So I was wondering, do you guys ever wonder, exactly what is the property of the matter? Because all these things seem wildly different, right? Water and plexiglass, plexiglass is very complicated. Plexiglass is basically made of the same stuff as we are, which is carbon, nitrogen, and oxygen. It's a plastic. Water is a lot simpler. It's just hydrogen and oxygen. Air, I guess, is simpler, but what would be the difference between, say, plexiglass and water and us that makes us opaque, but plexiglass clear, right?
Well, by the way, I was always wondering about this, and a number of years ago, I read H.G. Wells's The Invisible Man. Now, I think there's some film at present out, but it's probably not very good. It's probably just modernistic. I don't know. I'm a bit prejudiced against it, but I just remember that when I read the book a number of years ago, it was very scientific. He was, as far as I can remember, he said, look, if we can develop something which will vary the refractive index of the medium, well, then I can make myself invisible to people, but I can still be a solid being. So I'm not opaque, but the rays are just going through me as if there were nothing there. And it was all by varying the refractive index of the body, as far as I can remember.
Well, that's an interesting concept, except that refractive index still belongs to transparent objects. So if I were trying to make myself an invisible man, I'd have to have an refractive index to start with, right? But it goes down to the question of, what happens when an actual light wave actually hits any object. And I think even if you were like the Mr. Invisible Man, I think the closest you could come to would be you could be seen as being made out of plexiglass, right? It's as if you were made out of plexiglass, right? Because you'd still have a surface, or made out of glass, for example. I think that's the closest you could come to, that you could become a glass man. You wouldn't become like totally invisible, so you just can't go around. People would not be able to see you. I think they would still be able to see you, because you'd have a glass-like property, right? Light could pass through you, but because you're curved and you form like lenses and things like that you would obviously distort the light behind you. That
well, as far as I remember,
I mean,
it's years ago, but as far as I remember, Wells gave pretty good scientific reasons why what he was creating wasn't merely a transparent man. It was actually truly invisible man. Now, you have to consider, of course, as you say, what happens when a ray of light strikes a surface. How much of it is absorbed, how much of it is reflected, and how much of it is transmitted.
Well, we also have Harry Potter's invisibility cloak, which is another concept. Now, you could have an invisibility cloak. It's just that every single photon that impinges upon the surface of the cloak must exit at exactly the same angle as it would have if the cloak had not been there, right? See, if you could do that, then you would truly be invisible. I think that would be a more plausible invisibility kind of thing. And I think actually they've done something, things like that. Like they've got LED display, and if you put the LED display in front of you and display exactly the same thing that's in your background, then for someone looking at it from a distance, you would in fact be invisible.
Or they could do the converse. They can create you, let's say, by holographic means, and actually there's nothing there. If you put your hand through it, there's nothing there. But it appears to all intents and purposes to be a perfect replica of the entity or the person that they're trying to show up.
Let's see here. We got some more comments here. St. James is quantized. Well, we seem to have lost him, so maybe his internet connection fell off because he was there, and then he came back and he didn't have any sound, and then he's not here at all. So maybe, hopefully, he's joining us over in read-only mode in YouTube or something like that. And anyone can come and give us comments here if you want to participate. Says it won't take time because there is not time. Time is energy flowing, and waving is the least flow we can measure. There's not time? Really? Then what's my watch doing if there's not time? So I kind of have a problem with that, I suppose.
There's a book by Julian Barbour, Barbour, I think. He's on the science database, actually, as a dissident and so on, but that time is illusory. I read the book and I wasn't convinced by it. I thought he was straining a lot of arguments, but maybe Moser is saying something similar.
I mean, I kind of have a problem with this, actually the whole concept of flow of energy. Because that kind of makes energy primal, I guess. And I've been having some discussions with Cornelius about this whole, and with other people who think that matter is made out of, say, energy, right? So, and I have a gigantic problem with that whole concept. That energy is not primal. Energy is a property of matter, right? So you have matter. If it's moving relative to some other bit of matter, that is energy, right? So, but if you have two objects that were just sitting there, stationary, static, then I would say those objects have no energy. But if one is moving relative to the other, then you can say it has energy. That can be measured in joules.
Yeah, but there's potential energy. What about potential energy?
Potential energy, I would say, is kind of a fictitious.
It's the ability to create kinetic energy.
But that's really only still potential energy. I think the last.
Well, it's a form of energy. It's a form of energy.
It's not a form of energy. It's like if you look at what's going on, say in a gravity, if you got something orbiting, right? So the question was, okay, what is there an exchange of potential and kinetic energy in an orbit like Earth? The moon is orbiting the Earth. And I'd say no. There's no exchange of kinetic and potential. There is no actual potential energy. What you have is that you have two forces. One of them, centrifugal force, or actually inertia, is trying to make the moon go in a straight line. That's one force. And the other force is gravity, which is trying to drag the Earth down into the gravitational well of the Earth. And those are the only two things you have. There is no actual potential energy. The potential energy is really the measure of the force that the moon exerts on the Earth if it were to come to a screeching halt and you eliminate the inertial centripetal effect, right? That's something that you can measure. Like if you stop the moon and it came crashing down to the Earth, you can measure the energy at which that would happen, right? And that's what we typically call the potential energy. But
what about if you lift a hammer up over your head before you drop it? You've measured the potential energy change of the hammer, and then when you drop it, it gets converted into kinetic energy.
It's not converted. I would say that as I put a calculator over my head, right? It's just resisting the gravitational force of the Earth, right?
Well, but you have a measure of the potential energy.
There's no energy.
You have a measure of the potential. You've changed the potential energy.
If I put it higher, it just has
you've measured it.
Further.
You've got Hg. It's simple first first semester physics.
And you've expended that energy in moving the calculator to above your head.
Yes, you have. I'm just saying that's maybe a controversial position I'm taking, that basically potential energy is like a calculated value. It has no actual physicality.
So is kinetic.
Versus the amount of energy that might be contained in my hot dog or something like that. That contains real amounts of energy, right?
Well, if you've raised the temperature
you
of
could say
it,
that's potential energy, because certainly the hot dog is just sitting there, doesn't get energy until I put it into myself and break it down, right? That could be. So I think it's kind of superfluous. I mean, that's my position. I'm saying that basically it's a fictitious energy. You can measure it if you want, but it has no actual physicality of any real significance. You really need to be looking at the actual forces involved and talk about those rather than potential energy. Although the whole potential energy discussion is kind of interesting. I mean, maybe I'm wrong, Jim. What do you think? Am I wrong? Am I just like, saying that potential energy is a fictitious property?
I don't think
that doesn't mean it doesn't occur, but it's just calculated property.
Well, then I guess there's no such thing as E equals MC squared.
No, why would that mean? Of course there's E equals MC squared. Why would that?
That's the potential energy released into kinetic.
All that means is that if we completely destroyed some matter, we would get energy. That's not. I don't know what that has to do with potential energy.
Well, the law of conservation of energy basically says that the potential energy plus the kinetic energy is constant. So if you increase one, you decrease the other, and you can convert one into the other.
Well, I would guess that would go back to my other postulate, which is that matter is absolutely converted, and in the case of E equals MC squared, there is actually no conversion of matter in that happens. When a positron and electron come together and they so-called annihilate, there is actually no loss of matter. So it's not that you're taking matter and had potential energy and in the form of matter. What's happening is that
I happen to agree with that. I think that the matter that we call particles gets converted into essentially the particles of the ether that we can't actually detect individually.
Yeah, I think that too, but you still have to explain why we see amount of energy come out. And I explain that as being like this. See, when my two hands come together, they generate sound and heat energy, right? Because you've got these two things moving together at high speed. When they collide and they stop, that means that the kinetic energy can no longer belong to my hand because my hand has stopped. So conservation of energy demands that energy goes somewhere, right? And that somewhere is it gets released in the form of my hands getting shocked, and heat and sound, but that energy is conserved, right? It didn't disappear. So when a positron and electron collide into each other at very high speed, that kinetic energy cannot just disappear. It has to be released. I mean, even if it was a slow speed collision, still the kinetic energy has to be dissipated somehow. And that's what we observe in E equals MC squared. That's just an energy dissipated in the collision. Really, E equals MC squared applies to any two objects that are colliding into each other, whether it be two electrons and positrons, whether it be two cars. We have two cars hitting each other at 50 miles per hour. The amount of energy released is according to MV squared. Really, that's what it is, right?
Well, it's a half MV squared, really. It's a kinetic.
Well, you've got two cars, so it's 1/2 MV squared for one car plus the other 1/2 MV squared plus the other car. So when you release all the energy, it's like two cars hitting a brick wall then the total energy is mv squared, right?
Well, I don't know if one is stationary, you know, and the other is moving towards it. You have two equations. One is a half mv squared is dissipated, and the other is that there's a conservation of momentum. So if this is stationary, the momentum, the mass of this times the speed, is equal to the total mass, the combined mass, times the speed of the composite element.
No, I think it's simpler than that. You know, the kinetic energy formula, E equals 1/2 mv squared, right? So if I take a car and I drive it at 50 miles per hour into a brick wall, an unmovable brick wall, then the amount of energy I would expect to come out of that collision is 1/2 mass of the car, 50 miles per hour squared. I would expect that. Now, in the case of two cars colliding into each other, now essentially they are, because of the same mass, they are essentially hitting the brick wall, right? The deal is the velocity goes from 50 miles an hour to 0, right? Whether you're hitting a immovable brick wall or whether you're hitting another car, it's the same thing, same effect. Your velocity goes from 50 to 0, right? So it's like two cars hitting brick walls. So if you take the total amount of energy of the two cars hitting the brick walls, you'd have 1/2 mv squared plus 1/2 mv squared for both of the cars. The total amount of energy is mv squared. So that's what I'm saying, that this whole formula, E equals mc squared, that's exactly the same formula for any two objects colliding into each other of the same mass, right? They have to be the same mass so that when they collide into each other, they come to a grinding halt, right? Because if one was significantly more massive than the other, then it would actually still go in one particular, you'd still have some kinetic energy. But if they're exactly the same, then they all come to a halt, right? So it's no, you know, you don't need tensor calculus to figure this out. It's just simple third grade addition, right?
But the formula is meant to be more general than that. It's meant to be for any variation, any masses, for, as I say, for one element just smashing into the brick wall. It's meant to be very general. You've given one example where you have equal masses, and if you add the two kinetic energies, you get the same thing. But that's just one case, really.
Yeah, it's a very special case. But in the case of electron and positron running into each other, then you can see why it would generate that amount of energy. Now, if you look in the formula, why is the speed of light even in there, right? It could have been any other constant. It could have been the energy equals m pi squared or something, right? It doesn't have to be c squared. It could have been any other constant, but it is in fact the speed of light. So what is that constant? What's the speed of light have to do with the so-called, say, potential energy in that collision? And I would say my answer to that question is that when you have a positron electron hitting towards each other, and if you do the calculations, you can see that the force between a positron and electron generated, as soon as they get within some, immensely small amount distance away from each other, the amount of Coulomb force is so strong that it will accelerate it to the speed of light, right? And if the speed of light was not an actual physical limit, it would probably even exceed the speed of light. But the fastest they can head at each other is the speed of light. And I believe that at the time they actually impact each other, that they actually gain the speed of light. And so the velocity of the collision would in fact be the speed of light. So the general formula is mv squared. The energy released by two objects colliding into each other of the same mass is mv squared. And the mass of two positrons and electrons accelerated to the speed of light is mc squared, right? So it's not very complicated. It's just simple elementary third grade fractional math, right? 1/2 plus 1/2 equals 1, right? So,
Well, the
yeah.
units, of course, of mv squared are energy, so it's not surprising that is the case. But I tend to look at it maybe from a different angle. I conceive of these reactions taking place in the ether, if you like, with certain discrete properties. With we talked about it earlier, the permittivity and the permeability, and I consider mass to be, you could say, a condensation of the etheric energy. So I
I hate that concept.
I know you do. I know you do. Well, I'm not saying one is converted to the other, but I think it's a concept I sometimes use, because I prefer the equation m is equal to epsilon naught mu naught E, because that actually shows the relationship, how masses, if you don't like the word condensation, use something else. It's a sort of another manifestation of the energy, but it's related to the properties of the ether, which are permeability and permittivity. I think the formula equals mc squared, I don't like that formula at all. I think it's very misleading and simplistic, and it mightn't even be true, by the way. It could be that despite your simplistic explanation there with respect to you, I think E might equal n mc squared, where n is a factor perhaps which is less than unity. Like be 4/3 or something. So I'm not sure about that. I don't think we've proved that.
No, actually, they have proven that it's not true. See, now it's very difficult to measure loss of mass, right? Because the hypothesis is that any mass lost is converted into energy according to E equals mc squared. Now that's relatively easy to measure when you're colliding positrons and electrons. But if you're talking about like atomic matter, so in lithium can decay, and it's one of the few reactions that you can precisely measure the amount of energy that comes off this thing. It's very hard to measure the amount of energy that's coming off and say an atomic bomb, where there's a heck of a lot of energy there, but how much, right? You can't tell precisely, because there's just too much going on there. But for lithium, that is very simple. It's very similar to like a positron electron measurement, and you can put sensors around it, and you can precisely measure the amount of kinetic energy that is coming out of the decay. Now, when they do this, they find out that energy does not, in fact, equal the difference in mass c squared. That's off by like 20% or something like that.
Oh, well, that's interesting. I haven't seen those recent experiments, and maybe you could give us a link to that at some stage. By the way, Bob Gray is asking you, can he be allowed in? But anyway, the first experiment
back here too.
Yeah, I just saw that now. The first experiment, James is still there. The first experiment, which was meant to have verified E equals mc squared, was the 1931 Cockcroft-Walton experiment, where they bombarded lithium targets with protons, and they got alpha particles. Now, and they said, that verified E equals mc squared, and Einstein said that as well. But I had a look at the original paper of Cockcroft on this, and he said, we estimated the energy from the scintillations in the counter, and it appeared to me that it wasn't measured precisely. It could be 20% out, indeed.
Yeah, I think that's the same experiment.
Those experiments that you've referred to.
Yeah, I think that's the same experiment with lithium, because that would be on another precision measurement of E equals mc squared. As I said, is very difficult. Except
but I don't think it was a precision measurement. It was an order of magnitude experiment. They found that the energy coming out was approximately the same as energy coming in, accounting for the difference in mass. But they didn't measure it exactly to 5 decimal points.
Yeah, I think they have done that, and that when they did, it's like, oops, it's not exactly the same.
That would be interesting, by the way, because if there were papers, which there are, saying we've done modern experiments and we found E exactly equals mc squared, well, then I would be prejudiced. I would be skeptical, because I would say they're just really twisting around experimental results to give what is the established, politically correct viewpoint. But if there's some modern experiments that say it's 20% out, I would certainly pay a lot of attention to those, because that they would be going against the mainstream, and I'd like to see why they say that.
I think they're probably saying for because we give Einstein a lot of leeway that being within 20% is close enough, right? That's the only thing I can figure, right? Otherwise, we see this big thing that E does not equal MC squared, right? But it doesn't. In my thinking, you can only really precisely calculate that in the case of a positron electron colliding into each other, which is a complete conversion of the kinetic energy into the measurable gamma rays, right? When you're talking about atomic matter, now, atomic matter, clearly when you add it up, doesn't quite add up to if you had just taken all the protons, individual protons and electrons, and weighed them individually, right? And that is said to be the binding energy, right? So, and very difficult to measure precisely, right? Not unless you've got very careful things to catch everything that's going out and measure everything precisely, right? But in my world, mass is not an inherent property of a particle. Mass is due to its interaction with the environment that it is immersed in. So I'm thinking it's immersed in a sea of particles. Mass is just an expression of how much resistance it takes to accelerate that particle through that sea of particles. And you would think that there might be some geometric dependency on that number. So it's like if you took 10 ping pong balls and you measured the amount of energy it takes to move the ping pong ball through, say, air, and then you glued all the 10 ping pong balls together and you measure the amount of force of energy it takes to move that through the air, you might think that it might be different. It might be less than 10 individual ping pong balls because it's presenting less surface area to the direction of movement, right? So I'm thinking a similar thing may be in works here, and that it should be more of a geometric kind of argument depending on the shape of the atom. But it would seem that, still in general, in bulk, this whole E equals MC squared thing seems to generally hold, right? If you're not being super picky about it, as long as, 15 to 20% doesn't bother you, then it would seem to be accurate enough. So I still can't quite reconcile that, which is why is it that we have this binding energy that's dependent upon the difference in mass between various components of the atoms, I suppose. That's still something I'm kind of looking at there. Let's see, we got some other comments here. Here's another interesting question from Lucer. It says, would there be time if everything stopped in the universe with nothing moving? Who wants to take that one?
Well, there wouldn't be a universe then.
There wouldn't be a universe? Why would you say there wouldn't be a universe? Certainly there'd be the universe.
Universe is defined as whatever things are here now, and these are moving. If you stop it, then you've changed its properties so drastically it wouldn't be universe.
No, I would disagree. I would say that if time stopped in the universe, it'd be like this. Okay, but I'd still be here.
No, because you're made up of atoms, which are dynamic. Atoms, molecules, elementary particles, they're all open system, nonlinear, dynamic systems. You
Yeah,
stop
but you
that.
could stop them.
No, then they're not open, dynamic systems.
So
But stopping must be relative to something. You're actually saying it stopped relative to the dynamic system. Its speed is zero. So
I mean, certainly we
there
can
is an
stop
entity there.
individual things, right? I can stop myself. I can stop my car. I can stop a lot of things.
That's illusionary. You're not stopping anything. Stop
Oh,
a
sure
wave.
you are.
Stop an electromagnetic wave.
But I can
While
stop
it's
my car.
while it's traveling, you can't do it. Stop the jittering of an electron. You can't do it. If you do that, it's no longer an electron. Because an
sure it is.
electron, no, it's not, because an electron has a dynamic property, i.e., the magnetic moment. Stop that. It no longer has the magnetic moment. Well, it can't be an electron then. It's
Oh,
it's one of these nonsensical questions that seem reasonable, but it's not. Like questions like, I wonder what's outside of universe. That question may seem reasonable, but it's nonsensical. Because by definition, universe includes everything. They can't be an outside.
So I think this is a nonsensical question. So would there be time if everything stopped in the universe? Nothing moving.
There wouldn't be a universe. So you could not have.
I'm always happy to consider, four-dimensional system like X, Y, Z, T, or something like that. And I mean, the same question would apply if one said, suppose no object moved, would there be space? As if that in order to have space, you have to have objects moving within it. And the same thing here is there's an implication that in order to have time, you have to have elements which are varying in the spatio-temporal continuum. But I don't think that follows. To me, time and space are absolute concepts. I'm getting a bit philosophical now, and we could argue about that. But to me, they're absolute. They're independent of what motion or otherwise is occurring within space-time.
Well, I'm going to put a stick in the ground. So I'm going to answer this question directly. And I would say, yes, time would be stopped if everything in the universe stopped moving for whatever reason. If God just simply declared, press the pause button on the universe and everything stopped moving, then the entire universe would not have the concept of time. Time would not exist if God did that. Going back
Neither would
to
awareness. Neither
Go
would awareness. Neither
Yeah,
would anything. Universe wouldn't exist, and you wouldn't know that time stopped or did not stop, etc. It just, to me, it's a nonsensical question.
There wouldn't be flux, but I dare say there would be time. I mean, again, it's the old Grecian paradox. Who was the one who said that you cannot step in the same river twice because the river is flowing? So that was an indication of flux. Things are changing. And you're saying, well, if the river were frozen, you could step in it twice or something like that. That's true. Flux is occurring, and flux would stop in that case. But time, at least according to my provisional definition, would still exist. And you would say, well, nothing is changing in time.
No, I would still put my stake in the ground and declare that time would stop.
The more important question is it relative?
Is what relative? Time?
Yeah.
No,
Well,
time is absolute.
Yeah, well, I think most of us have views about that. Probably most people on the conference here would say, well, I'm not sure. They would probably say it's not relative. I certainly would say that.
I'd say it's not
Well,
relevant.
I'm just saying that's a more interesting question about whether time would stop or not.
Well, I think it goes to your definition of time. For example, my definition of time is that time is measured as the change of state of any given state. So if I had a board with 3 pegs, and if you're talking about time with that, then you could measure time that you would see one like ring go from one ring to the other. And so that pegboard has a concept of time because you can see state change. Now, if you were to just not move anything on that pegboard, then I would say, so far as that system is concerned, right? Because that system time is stopped for that system. Or if you had a
But-
computer and you just, stop the clock and you would see everything in the computer freeze up, then I would say the concept of time for that system, because I think time belongs to a defined system, right? Now that defined system could be the whole universe. It's very hard to conceive of stopping the time in the universe. Not unless you could conceive of like a god-like super being who's running the universe, and time would not stop for God, but God could like press the pause button on the universe and time would in fact stop for
a measurement
anyone in the universe.
a measurement device of time is not time. Just like a pressure gauge, which measures pressure, is not pressure. So any device that you come up with to measure time, like a pegboard and loops going from one peg to another at a certain rate, that is not time.
No, I'm saying it is time. That's what I'm saying.
Then there is a pressure gauge pressure. Because it is
Effectively,
measuring.
Yes, it is. It's a
So-
measurement of what you're going after. So it's a definitional. So a pressure is the thing that you get out of the pressure gauge. Yes, that's kind of what it is. Especially with time. I mean, it's less obvious with pressure, because pressure corresponds to an actual physical thing, which actually changes when the pressure changes inside. But time is something which is strictly measured by our instruments, right? It doesn't have, I would say, any other physicality, right? It's something which is strictly measured by your instrument. It is as if pressure could only actually be measured by your pressure gauge, right? And there was no other definition or other way you could think about it. And time is one of those things. Time is measured purely in terms of our instruments. And those instruments have moving things, and it's a measurement of the rate of that change. That's why I think that when you talk about time, you need to have these very kind of firm definitions about that. It's the rate of an observable change in any system. Is kind of the way I look at it. So,
But
that's an
time seems to
interesting
be the only dimension that you are attributing this to. I mean, if you had no forces in the universe, if you had an equiforce universe, you wouldn't say it ceased to exist, or you just say, well, the pressure is the same everywhere. You wouldn't say the universe has ceased to have any meaning. But if it's constant in time, you say it has. You're attributing something very special to time, which is not attributed to other quantities, despite the fact that you have said to Bob that a pressure gauge is pressure, which I would dispute. But you were forced into saying that.
I'm just saying that the time in particular is like that. That it's literally something that can only be measured by our instruments.
Measured by, but is not the measurement instrument.
I think
Here.
the reason that people scratch their heads so much about time is because of Einstein's special relativity that's saying, time dilation, and it's not absolute. If it were absolute, it would just be something that was there. You wouldn't have to worry about it so much.
So he wants to change the topic here. He says, how is a radio wave emitted? What is emitted? Where does that energy come from? If that comes from an electron, what happens to the electron? Well, anyone want to take that one? How are radio waves emitted?
I mean, it depends what he means by emitted. If we take that there's a varying electromagnetic field.
I think that's pretty clear. You've got your CB radio. You talk into it. Something comes out of the antenna, which is received by someone else's antenna. That's a radio wave emitted, right? That's what he means, right?
But do you have to go that complex? Just take 2 electrons, and it's the force on one electron due to the other electron. Now move one of the electrons. The force experienced by the other electron is going to change. That's all you're measuring. When you talk about the CB and the antenna and stuff, it's just a lot of electrons. So there's an accumulation of force on the receiving antenna electrons.
Well, that's an interesting concept, right?
Just the force. You're just changing the force.
Electrons here. We know that they've got a repelling force between them. So if I go and I wave this electron around, we would expect the other electron to wave around in sympathy, right? Because it's experiencing a variable force, right? We wouldn't expect that one electron would be waving around here and this other electron would stay stationary, right?
Right, and then they're confined to a non-conductive medium, the antenna.
But you see, the radio waves travel like humongously wide distances. So while I could see that happening for relatively short distances, but although the electrostatic field, I guess, has infinitely distance, and it drops off 1/r². So maybe that isn't a complete argument, but.
And the analogy with resonance or with, say, musical sounds, if you bang a tuning fork and you get a sympathetic resonance in a string or something like that, it's the same sort of thing. But I'm not sure if he's asking that question as well, or if he just is so amazed because radio waves seem like magic, but other things that we see in life, like resonant frequencies and things like that, are analogous to it.
It is magic.
Yeah, well, certainly over 100 years ago, people thought it was magic.
I don't think we still understand it completely. So I think you could still call it magic. We don't really understand what the heck is going on.
Yeah, people, it's true that you can get a bunch of radio people, and Harry could probably tell you that we know a lot about how to make radio waves and how to make good antennas and whatnot, but we really actually still don't know what the heck a radio wave, or in fact what light is. Really, that would still be up in debate. Now, I would argue that the reason why that is so is because our denial that there's a medium of transmission for those waves, right? We know that they act like waves. They can be canceled. They seem to have phases. They do everything that sound waves can do. Except that if we admit that they're a wave, then that requires a medium, but a medium that we have not yet detected. But we rejected the medium because the Michelson-Morley experiment saying that there is no medium. Some adherents to Einstein think there's no medium. Himself said there was a medium, but he said it didn't consist of any parts. And that just doesn't make any sense. So there's Musafir's question of directly, which is, what is a radio wave? What is being emitted? What is going on there, right? And this is the way I see it. Okay, first of all, in order to have a wave, you need a medium, right? So hits your face, some C of some particle. It's a positive. So that's step one. Step one is fill your space with some physical medium so that you can have a wave, right? So step two, what is a radio? It says you take a voltage and you vary it on a piece of wire. That's it, basically. And you oscillate it back and forth. So you have a voltage, say 5 volts. You take a piece of wire, you attach it to a sinusoidal power source of 5 to 0 volts. That's your basic radio transmitter, right? So what is that doing? Now, in order to transmit a radio wave, it actually has to be oscillating. If you just put 5 volts on and you just leave it there, you get no radio wave. Any fixed voltage will do. But if you oscillate it, that's the second requirement for radio wave. That it must be, you have to have this arrangement where you have a varying voltage going out to a piece of wire. Anything like that transmits radio waves. So what's going on there? So voltage is electron pressure. It's an expression of the electron density of the free electrons in the wire, is what it basically is. So if you've got 5 volts, that's 5 times as many electrons as, say, 0 volts, right? That's what it is. So when you oscillate between 0 and 5 volts, you are varying the electron pressure. Now, what happens to electrons inside the wire? When they experience more pressure, I think that they kind of blow up like a balloon. And I think it pushes the electrons on the outside of the wire, literally out, right? Physically, as into a kinetic action, right? That physically, that as you vary the voltage between 0 and 5 volts, that is actually physically, if you were to look at it with a microscope, could physically see the electrons moving up and down in sympathy to the varying voltage, right? So you've got these kinetic actions of electrons going literally out of the surface of the metal, out into space. And that's exposed to this whatever medium that you're talking about, right? So as you get all these things going, they will start pushing out on the medium, and that will generate a pressure wave, right? So you've got a whole surface all of a sudden all the way going up. That generates a pressure wave. That pressure wave then can travel across space, right? And that's what's actually traveling across space, a pressure wave of this medium of, say, positrons or electrons or whatever you have. Now, on the receiving end, I would say that you have a piece of metal. It's got electrons on it, and they're at neutral voltage. And when you see this wave of pressure wave come and hit your antenna, it's going to push your antenna. So literally, as a kinetic action, it's going to be pushing in the electrons from the surface of your antenna. That creates a slight pressure increase on your antenna. And any pressure increase can be measured as voltage, right? It's not much voltage. I mean, it's much less than from the transmitter, but it's still impinging upon the electrons. It's still creating a voltage. That voltage can then travel through a wire to sensitive amplifying equipment, and then can convert it right back into the original signal. So that's my idea about how radio works. Ian, what do you think? Plausible? Not plausible? What do you think?
Well, I mean, it's all plausible, and it's a jolly good try to give a mechanical explanation, if you like, about what's happening. but I mean, you can look at various other things. For example, there was this public house in Britain. It was meant to be the oldest public house in Britain, and it was meant to be haunted because people would sleep in a room and they would get sounds, so on, in the nighttime. Anyway, so they did some experiments, and they put up some recording equipment and so on. And yes, they got sounds, and they couldn't make out what the sounds were. They first thought it was Welsh rather than English, but they analyzed it wasn't. And then actually it appeared to be sounds backwards. Backwards. They played it backwards and they got some sounds. Anyway, the theory, which was put out eventually, was that you had, this pub was well over 1,000 years old, and you had these walls with little bits of mica in them, and it was a very damp atmosphere. And what would happen is, in the daytime it would dry out, and in the nighttime it would cool down, and the water vapor was effectively an electrolyte. And the wall was a system with the little bits of mica, which was producing a varying magnetic field, depending upon how the electrolyte varied in the daytime, and nighttime. And then the wallpaper was acting as a baffle. And So what you're getting is the varying magnetic field was giving a varying electrical field, and then that was being converted into sound by the variation of the baffle. So you're getting a very early recording device. And similarly, another example is if you had maybe a pot which was made in the Middle East some thousands of years ago. Well, the potter was spinning the pot, and he might have had a little stylus which was making decorations on the surface. But if he were speaking at that time, well, you could get the pot, you could spin it around a turntable now, you could put a similar stylus in, and you would get his voice back. So all these are sort of mechanical analogs of an electric system, of a tape recorder or of a gramophone disc. And you've just given an explanation, a mechanical explanation of the electrons of a recording device. But I always look in terms of analogy. You probably know this already. And I always basically look at the mathematical equations. And if I see that they are really using the same sort of type mathematical equations, I say, oh, goodness me, this is just the same thing. Just substitute electron for, for a piece of mass or something like that. And they're all similar devices. There's no reason why I know it's magical. It appears we can't see anything, and we don't understand exactly what's happening at the quantum level, and God knows what. But it is actually analogous to a mechanical device. And maybe a good intermediate position would be the vinyl disc, where you're actually having a magnetic vibration, which is being picked up by a cartridge as it's being transmitted to us and eventually to our ears.
So Musair has another comment here, is that you're talking about a single EM wave, a large one in radio waves, probably many running in parallel, created by every moving electron. I mean, I think that's a very important observation with radio waves, in that, we think of EM waves, they draw it as like this nice sinusoidal single wave going through space. But that's not the case. It's more like the waves crashing on a beach. That what you have is actually a wave front. Because like in that picture I gave you, you have the wire. It's a long, skinny thing. And if you imagine generating a radio wave off of that it would come off in like increasingly spherical shells off of that wire, and it would actually reflect the shape and size and direction of that wire. And that if you were to put a wire next door to it, it's exactly parallel, that it would catch all of that wave at once, right? But if you took the wire and you flipped it 90 degrees, then the wave would only impact just like a small, just the diameter of the wire, right? And so it would not receive the signal very well. And that, I believe, is the basis of polarization, right? So people like to think of polarization of like a rope through a picket fence, right? But I'm telling you that radio waves don't travel like a rope. They travel like waves on a beach, right? And so the thing that's being polarized is not this single wave, but what's being polarized is actually the entire wave front. It's the wave front which determines the polarization properties, you can't even speak of there being an individual EM wave in that case, right? It's like, is there an individual wave in the wave that's breaking onto the beach, right? It's a big, long thing, right? That's coming towards the beach, right? And you can't say that there's like, one thing in there, right? But I think he also wants to know about, say, photons, right? Now, so Musair has another comment here about, he's trying to understand how are photons emitted and how many for electron motion cycle. So we think electromagnetic, like radio waves, light waves, gamma rays, microwaves, we think that those are all kind of the same thing. But I would say that in the case of, photons in particular, like light waves, I think light waves, things which are generated by atomic processes, like we were talking about the hydrogen atom and how when the electron transitions, you get this very specific spectra, and those are visible light waves, that I think that those are very different those are highly quantized. I would say that in a radio transmitter, it's not quantized, that you could have basically any amplitude you want, right? I think that's pretty continuous to the extent that, you know, time is quantized. But I think photons are different because they are generated by the quantized actions. It's like, what happens when an electron goes from level 4 to level 1, right? When it drops down through this potential difference, it releases a specific light wave, right? Now, the only way I can think of that happening physically is that it's like dropping a ball on your foot, right? And but it's kind of like if you were to throw a I don't know, like a tennis ball in a small box. So you throw a tennis ball and it kind of bounces back and forth according to the amount of energy that you threw in. So if you threw in the ball faster, it would bounce faster, bounce back and forth faster. If you threw it in slower, it would bounce slower. So I'm thinking that when the electron actually transitions from top to bottom, it actually hits the proton. The proton jiggles back and forth. It's that jiggling of the proton that then is impressed upon the rest of space surrounding it. And that is what goes out into the world. But it only goes out not as like a big giant sound wave that has this big spherical output. It actually goes out as a single wavelet, I guess. It's like if you were to line up all your billiard balls in a straight line and you hit one end and all the wave travels perfectly through the line of balls, that is the kind of thing that I'm thinking what a light photon is. It travels only through the single line of balls. And because it does that, it doesn't spread. So I think that's what happens with, say, laser light. So I think laser light does not obey the 1/r squared, you know, decrease in intensity. That it's pretty much as intense from 1 foot away as it is from 10 feet away. You know, it still produces that very bright spot. So, and the reason why it can do that is because those light photons are not dispersing. They are traveling with exactly the same energy and impacting the surface the same energy, whether you're 1 foot away or 10 feet away, or 1,000,000 feet away, or 1,000,000,000 light years, just like we can see the stars in the sky. But each one of those little photon wave, and it's still a wave, I still believe it's a longitudinal compression wave, just like going down a row of billiard balls. That's a longitudinal compression wave, but it's very directional. But because it does that, they travel like bullets, which I think is the main cause between this whole dichotomy between wave and particle, because the photon travels like a particle, as if it were a particle. It doesn't travel like conventional wave, where it spreads out in all directions through a medium. It is non-dispersive. But that's kind of my answer for Tim Gusser. So you asked some very good questions, and as dissidents, that's kind of the things that we ponder and try and come up with some answers. But I believe that we are at the end of our time here. So I thank everyone for participating. I think today we started out with a discussion of time because Ian managed to make it here on time despite all the crazy daylight saving things that are going on. So good job, Ian. And we got into this whole topic of, what is time, specifically, what's the definition of time? If you stopped everything in the universe, what would happen if you did that? And then I think we mostly did that. I think we were mostly talking about what time is. We did a little discussion on what potential energy is. I kind of think it's a fictional property. And I tried to explain why I thought that was. Let's see, what other things did we get into? We didn't get at all into the coronavirus. So, but Gusser reminds you that you should be taking 3,000 milligrams of vitamin C or 2,000 milligrams an hour if you're sick, right? So we'll all try and keep that. It's like the entire state of Washington is in a virtual lockdown with all the schools shut down, all the theaters shut down, all the museums shut down. You can't even do a staycation now here, right? We're all stuck at home. But that's the latest report here from the Seattle area. But that
I
will do it.
noticed that President Trump has curtailed travel from Europe, 26 European countries, but he's accepted Britain and Ireland. And I don't see any reason for that, apart from the fact that we're all English speaking or something. It seems a bit anomalous.
Yeah, we like English speaking
I
countries.
think so, yes.
If you're English speaking, you couldn't be that bad.
That's it. That's it.
All right. Well, we'll see what happens. I probably by this time next week, the state of Washington will be completely locked down. So we'll see what happens. But that will do it for now. Ta-ta.
Thank you.